Hi there. Thank you for clicking on this video. In this video, we're going to focus on multiplying radicals, and we're going to cover a little bit of division. Division has some rules to it that kind of would make this video very long to cover all of it, but we will introduce some simple division in this video. If you're looking for a division that involves rationalizing the denominator, just be advised that is going to be in a separate video. As always, give this video a thumbs up if you find it helpful. Drop a comment or a question below and check out the practice set for this concept. Now, let's do something a little atypical. We're going to start with the key idea. Typically, if you've watched a lot of my videos, you know that I'd like to start with reviewing what we know, introducing the vocabulary. I'm really big on laying the groundwork for why what we're about to do is what we do. I don't usually start with the key idea, but this time we will. Okay, so the key idea is this. If you have the nth root of a times the nth root of b, that is equal to the nth root of a times b. In other words, you can simply multiply what are called the radicands. Okay, so the a and the b, the vocab word for that is radicand. It's the word for whatever is underneath the radical, and we can just multiply them together and then take the nth root, whatever that might be, of the product. But why? Okay, so if you've watched any of my videos, I'm not going to just like go around and give you a key idea and be like, okay, now just do some problems, plug into this formula. We want our key concepts to make sense and be grounded in what we know to be true. Math should never ever feel like voodoo. It should never feel like magic. I tell my students it's magical, but it's not magic. So we don't want it to seem like, okay, we can just do this where we multiply the radicands, where when we're adding and subtracting, we can't add the radicands. So we cannot add them, but we can multiply them. The why behind that should make sense. So if you looked at my video, watch the video for adding and subtracting radicals, I make the argument and the justification for why we cannot simply add them, okay, why they have to match. And now we're going to have the multiplication where we can, and there should be some sense behind why that is true. All right, now I want you to recall this law of exponents. This is that if you have a product raised to a power, that is equal to each of the factors raised to the same power. Now, just for like an example, we'll do a, b, and we'll say ab to the third power, okay? And what that means is ab times ab times ab. Okay, so raise something to the third power means to use it as a factor 3 times. Now, keep in mind that this is all multiplication. All right, so that's a times b times a times b times a, like that's all multiplication. And you can multiply in any order you want. So you can multiply all the a's and then multiply all the b's. And then you can see that that is actually equal to a to the third times b to the third. And hence the exponent on the outside would apply to each of the factors inside. And it doesn't matter what the exponent is. I did it with a 3, but you can do that with a 2, a 4, a 5, whatever you want. You just have a whole lot of a's and b's floating around. Okay, and that's how we justify that law of exponents. Now, in the last lesson, we learned that radicals are actually rational exponents. If you missed that lesson, or maybe you're watching this video out of order, because typically when I've taught this, I've taught the operations on the radicals before I've taught the rational exponents. Okay, if you're doing it out of order from the way that I've done the videos, I want you to check out the video up here. Okay, I'm gonna put the link right there, okay, for you to be able to click on that video and watch it. Okay, so we have established that radicals are actually what we call a rational exponent. This means that the properties of exponents also govern how radicals work. In short, it means we can take this and we can apply it to radicals. Okay, so let's connect the dots on that. If you have the nth root of a times the nth root of b, that is a to the 1 over n times b to the 1 over n. Now, that's where if you haven't done a lesson on rational exponents, I could have just lost you right there. Not a super difficult concept, but it is one that somebody does need to teach you. It's not something that you're just going to come up with on your own and say, well, that clearly makes sense. It does make sense, but the reasoning behind it, we do need to walk through it. Now, what I'm going to do right here is apply that law of exponents, which says that that is the same as ab to the 1 over n. Now, what I did there was I applied that law of exponents. I just did it in the reverse order. So on the previous slide, we had ab to the m, and we said that was a to the m times b to the m. This time I have it with it split up, and I'm going to merge it together, okay? But it's the same law. And then if I take that and change it back to a radical, well, we have the nth root, and now the thing under the radical, like we could think of it as ab to the first power. But of course we don't need to do that. So it's just the nth root of a times b, and there's our key idea. Okay, so the nth root of a times the nth root of b is equal to the nth root of ab, and now you've seen the dots connected, and you can also see why I wanted to detour and do that lesson on rational exponents first before we tackled multiplication, because it gives us the tools we need to make sense out of the rule, and we're not just trying to memorize a rule because your teacher or some total stranger on the internet just told you that that's what the rule was. Right, now a few things to note about multiplication of radicals. First of all, unlike adding and subtracting, the radicals do not have to match for us to multiply them. If you were doing the square root of 3 plus the square root of 5, we would have to say that we cannot add those together because they're essentially unlike terms, but we can do the square root of 5, 3 times the square root of 5, and that would be equal to the square root of 3 times 5 or the square root of 15. All right, and that's something that now that we've looked at it in terms of exponents, we can make some sense out of that. If you were to change these over to exponents, you'd have 3 to the 1/2 plus 5 to the 1/2, and we can't add exponents of unlike bases. It simply does not work. And we can simplify them before or after the multiplication. So you're welcome to simplify the radical before you do the multiplication, or you can multiply it and then simplify at the end. If you do it beforehand, you might have to do it twice. So you might simplify before you multiply, and then you're going to have to simplify again after you multiply. It's really a trade-off. If you do it twice, there'll be easier simplifications because you'll be dealing with smaller numbers or expressions. So that can be a little bit easier, but you'll have to do it twice. If you do it afterwards, you'll only have to simplify once, but you might be dealing with something that's much yuckier to simplify. Kind of pick your poison on that. You can kind of take it problem by problem. So I've got 3 examples to work through just to show you how this works before we say, hey, go do some of these on your own. So this first one is 2 root 3 times 3 root 5. And I just want you to remember that this is multiplication. So this is 2 times the square root of 3 and 3 times the square root of 5. So really, you've just got, a bunch of, I don't know why I'm rewriting it. That's weird that I did it, but it's just a bunch of multiplication. And that means that you can kind of gather the things that are outside the radical and gather the things that are inside the radical together. Normally, we don't do that. We would just say, hey, multiply the stuff that's outside the radical and then multiply the stuff that's inside the radical. And you don't rearrange it, but it is maybe nice to see one time, why we can do that. 2 times 3 is 6, and then I just did this on the previous page. The square root of 3 times the square root of 5 would be the square root of 3 times 5, which is 15. And the square root of 15 cannot be simplified, so that would be the end of the problem. Typically, you would skip that, and you would just go straight to the answer. So this would be a 1-line problem, do not show any work kind of problem. Now for this second one, we have 4 cube root 4 times 3 cube root 4. There we go. All right. And in this example, we would be multiplying the stuff outside times the stuff inside. And you could, no, you can't simplify these. So yeah, we're just stuck doing what we're doing. So 4 times 3 is 12. And then we have the cube root of 4 times 4, which is 16. But now we've got to check and see if that is simplifiable. So I'm going to come down here and just cordon off some scratch work. We've got the square root of 16. The 16 factors into 4 times 4. And each of those 4s factors into 2 2s. So we have 2 times 2 times 2, you get it. And we're looking for a group of 3 because that is a cube root. And so that would be 2 cube root 2. So up here we have 12 times 2 cube root 2. And then 2 times 12 is 24. So that ends up being 24 times the cube root of 2. The extent to which you're showing your scratch work, that is up to you. I can simplify that in my head without showing any scratch work, but students, I've been doing it a lot longer than probably anybody watching this video, so show more work. I certainly didn't show like no work the first time I did it. All right, last one here, we have the 4th root of x to the 5th times the 4th root of x to the 3rd. And I'll show you this one 2 different ways. So if we just multiply the radicals, we'd have x to the 5th times x to the 3rd. Now, just like this is a quick little thing here. So I've got 5 x's, so 1, 2, 3, 4, 5, and then 3 more, and you can see that would be x to the 8th. Okay, x to the 8th. And now we'll do the simplification here. This is 8 x's. 1, 2, 3, 4, 5, 6, 7, 8. And because it is a 4th root, we're going to be looking for groups of 4. And I've got 2 groups of 4. So that would be the 4th root of x to the 4th would give me x, and then we'd have another x. And so that would be x squared. If you wanted to do that a different way, you could do this. Okay, so x to the 5th would be x times x times x times x times x. 4. And we'd be looking for a group of 4. And so this would simplify to 4 times the 4th root of x times the 4th root of x to the 3rd. And then multiplying these together would give us x times x to the 3rd, which is x to the 4th. And the 4th root of, sorry, I'll copy that over again. The 4th root of x to the 4th is just x, leaving me with x squared. So one of those was just multiply it, simplify it once when you're done. The other one I simplified beforehand and then ended up again with something that I needed to simplify on the other end. I would take it probably problem by problem, which strategy you think is going to be easier for that problem, what's going to be easier for you as an individual. Now, I want to take a quick look at some simple division here. Like I said at the beginning of this video, division gets into the weeds with some very mathematician-y kinds of rules. But for some simple division, the same principle applies. And that's pretty much this. If you have the nth root of a over the nth root of b, that's equal to the nth root of a over b. And we could reason that out the same way, where you have something like this. That's a to the 1/9 over b to the 1/9, 1 over n. I don't know why I said 1/9. 1 over nth, 1 nth. The nth, 1 over nth, 1 over n over b to the 1 over n. And using the laws of exponents, we know that that is a over b to the 1 over n power, which of course would like kick us back over into the radical like that. So here's an example of one. And again, with the same as with the multiplication, you can simplify the cube root of 16 and then do the division, or you can do the division and then simplify. So we'll opt for that first one. That would be the cube root of 16 over 2. 16 over 2 is 8. And then you might remember from previous studies of things like the difference of cubes, you know that 8 is a perfect cube. So just to refresh your memory there. There we go. Okay, that's equal to 2 cubed. And of course, the cube root of 2 cubed is 2. You could probably do this, like just go straight there. Okay. And that is me in instructor mode, actually breaking it down further than it needs to be broken down. If you opt to do it the other way, you would do the cube root of 16. You would recognize that that is 2 times 2 times 2 times 2. We're looking for a group of 2, or sorry, a group of 3. So this simplifies to 2 cube root 2. And then if we wanted to do that, that's 2 cube root 2 over the cube root of 2. And of course, anything divided by itself is 1. So that would cancel out, leaving you with just the 2. Again, you got to pick which way you think is a better way to do it. When we do the practice set, I'll try to cover this again, where I do at least a couple of them both ways to try to meet the needs of whoever might be doing them the different ways. Now, we'll cover more division in the next lesson, which of course, at the time I'm recording this, I don't have recorded, but it's very likely that by the time you watch this, it is recorded. So you can check that out. And I will be sure to cover the concept of rationalizing the denominator in that lesson. The practice set will review adding and subtracting, as well as look at multiplication and this simple version of division. So just a heads up when you go to click on the practice set. Please don't forget to give this video a like if you found it helpful. Subscribe to the channel for more math help, and check out the practice set for this lesson or the other videos that we have on the channel, whatever is going to help you in your math journey more. And I hope to see you in a future video.